in the. So I will today and next week focus on why we measure flow and how we do, and I will introduce at first the very basic techniques, and then eventually a more advanced technique next week. Next week, I will also hopefully have time to discuss some of the results that have been obtained by collaborations at RIC as well as at LHC. I should stress in the beginning that there is so much. I mean, flow has been a dominating feature is a dominating feature of heavy ion collisions, and as such has attracted a lot of attention and has involved a lot of people, smart people who have developed magnificent techniques to measure flow, and so it's absolutely impossible to cover everything. So I will do my best to, I think, introduce the topic, and if I miss something or one of your favorite techniques, then I apologize. I should point in the beginning that there is some discussion of flow techniques in a book that I released in 2017. Some of you are already familiar with this, but I have a contract with Cambridge, and they asked me to mention the book whenever I make presentation. So let's start with this cartoon view of what we believe is happening in relativistic nucleus-nucleus collision. I'm sure most of you have seen this slide in some form or another before. And so we start here. So the time evolution is from left to right. At the left here, we have two nuclei that look like pretty much pancakes because of relativistic spatial contraction. And we'll discuss that a little more in a minute. So these two beams, these two nuclei approach one another. At Richt top energy, we're speaking of 200 GeV per nucleon. At LHC, when I created this slide, the energy was 2.73, but now we have achieved much higher energy in these collisions. So basically, these nuclei are traveling near the speed of light. Then they collide, they interpenetrate. Because they are so pancake-like, the collision or the traversing time, if you will, is very short. But a lot of the kinetic energy of the nucleons and in quarks and gluons within these nucleons are immediately converted into the making or the production of particles, which is illustrated here. These red, yellow, blue balls are meant to illustrate the production of pions, mostly kaons, and to a lesser degree, higher mass particles. And then these particles evidently will collide with one another. They will expand, and then eventually the system will break down, and these particles will stream out to our detector with upward of 6,000, even 10,000 particles in lead-lead collisions at LHC. So this is what we think is happening. This is what we know is happening. So I'm giving here two examples of experiments. On the left, Star, which I used to belong, and on the right, Alice, which I now belong to. Evidently, there are and were other experiments at both RIC and LHC, but this serves the purpose of illustrating what these collisions look like. So in both bottom pictures here, these are snapshots created by pattern recognition software that illustrate the charged particles that were reconstructed from the collisions. And you see lines of different colors and different curvatures, curve to the left, curve to the right. And this indicates that there are both positive and negative charged particles produced. And essentially, there's essentially a equal number of particles and antiparticles produced in these high energy collisions. So let's narrow the discussion a bit to talk about flow and why flow is important and why we care. So let's talk a little bit more about the geometry of the collision, because when it comes to flow, geometry is the dominating factor, and it drives everything that happens in these collisions in terms of collective motion. So again, we are here in the top. We see that we have the two nuclei, pancake shape, that have now that are now in full overlap. And what we understand is that as they collide and traverse one another, a significant fraction of the kinetic energy that these nuclei carry has now been transformed into particle production, or and has released gluons and quarks, thereby giving us a plasma, or some kind of fireball, if you will, that contains a large amount of energy. So a very large energy density, because there's a huge amount of energy released and converted, and it's at first sitting in a very small volume. So that leads to enormous energy density. And with a very anisotropic system, obviously it looks like a pancake in the longitudinal direction, whereas in the transverse direction, if we have a non-central collision, a collision with a fairly large impact parameter, as illustrated here, one nucleus going in the page, the other going out of the page, we have this overlap region here in a darker shade. And this overlap region now contains a vast amount of energy, and therefore there is a lot of pressure that will be, this will translate into a very large amount of pressure in this zone. And this pressure then is not acting in the same way in all direction. Obviously, in the longitudinal direction, the pressure gradient from the large density of the matter to the vacuum, it gives us a very, very large pressure gradient. Whereas in the transverse plane, you have along the x-axis here, you have a somewhat smaller but still large pressure gradient, and in the y direction in this slide, you see that you have also you will also have a pressure gradient, but the size of the nucleus in that direction, or the size of the overlap in that direction, it being larger, we have a slightly smaller pressure gradient. So this leads to a hierarchy of pressure gradient, as shown here, largest in the z direction, slightly smaller in the x, and smaller still in the y direction. And so associated with this pressure gradient then means that the matter that is formed will expand under these gradients. And so the pressure gradient along z being the largest, the expansion will be the fastest along z. And then the pressure gradient along x being what it is, then there will be expansion along x, and to a lesser degree along y. And so in the transverse plane, the fact that the gradient of pressure along x and y are different leads to an anisotropy in the expansion of the system. And this is essentially what we're trying to measure, and not trying, we have measured. And the idea is that we are interested in how this pressure gradient, how this large density gradient and pressure gradient is transforming into the acceleration of the fluid, the expansion, the transverse expansion of the fluid, and eventually the production and emission of particles in the x and y directions. Okay, somehow, there we go. Before I go into an actual discussion of the techniques, I think I should point out that there was a lot of work done to first establish the existence of flow, and then to develop techniques to measure flow quantitatively and do this better and account for effects that were not so interesting. So I should point out that first measurements of flow were done at well, if not the first, amongst the first measurements of flow were done at the Bevelak in California, and with techniques developed by Danielowicz and Odiniak. And then Olitro later realized that this anisotropy was an unambiguous indication of transverse collective flow. Beyond that, there were measurements of particle correlations also at the Bevelak, and eventually at the AGS, at the SPS, and so on. And then eventually people realized that along with this cumulative, if you will, or collective motion of particles, there were also other phenomena coming into play, so that we now call non-flow. And then so this came the realization that one needs to account for this non-flow and suppress it. In my view, the real breakthrough was accomplished by Voloshin in 1996, when he wrote, in the context of AGS experiment 814, I believe it was, he wrote the anisotropy in the transverse plane in terms of a Fourier expansion of azimuthal distribution. And this was really the very beginning, and a very successful beginning, of the development of measurements of flow, because this gave us a quantitative and mathematical setting in which these measurements could be done. And then later on, techniques were developed to reduce non-flow. Borghini and Olitro, as well as Voloshin, contributed to this. And then there were a number of methods, some of which were very fancy, such as the Li-Yang zero method, that were developed. But although fancy, it also had its drawbacks. And then another substantial progress was achieved again by Voloshin when he introduced the so-called sub-event method. And so in order to reduce non-flow correlations in the measurement of collective flow. Then Bilanchik and collaborators introduced the cumulants method. And even though these were very tedious to calculate at first, additional methods were eventually introduced to enable measurements of these Q cumulants. And this led eventually to what is now known as the generic framework that was created also by Bilanchik, and now is used by a lot of people in the Alice collaboration. Last slide on this historical survey is just to mention that after this development of the generic framework, there were also new techniques, new interests that were developed. And this led, for instance, to the creation of so-called symmetric cumulant, asymmetric cumulants, normalized symmetric and asymmetric cumulant. And then interest in the cumulant of symmetry plane correlation, interest in the study of linear and nonlinear effect in the measurements of Vn, and eventually also by Voloshin, event shape engineering, and so on and so forth. So, and this is continuing today. There are still new ways that people are looking at this. So clearly, you can already tell from these three slides that a vast amount of techniques and methods have been invented with different, variations and so on and so forth. So I will do my best to talk and cover some of the what I believe are the most important and most used methods. But again, as I said already, I will not be able to cover everything. So before we actually jump into the development of the technique, I want to remind you that we are not working in a vacuum here. This is not a new field of study or subfield of study. As I've said, flow was identified at the Bevelak, but perhaps the most exciting results were obtained right at the beginning of the star collider, the RIC collider by star in 2000 already and published in 2001. On the left is a measurement of the so-called elliptic flow that I will introduce in a moment as a function of the multiplicity produced in these collisions. And what became exciting at that time was the realization that the data in the highest multiplicity collision in this region here, the data seem to reach the level of flow, or V2, expected from hydrodynamic calculation involving no viscosity, so-called ideal fluid. And so this led to the notion that perhaps at RIC, indeed, we were producing a fluid that seemed to flow amazingly well with essentially no viscosity. And this led, in particular, Uli Heinz and several others to compare the data with various calculations. I'm not going to go in detail here, but again, just to show that with these calculations, Uli Heinz was able to reproduce transverse momentum spectrum, and he was able then to also explain the amount of flow that was observed. And most importantly, he was also able to reproduce the hierarchy, or the progressive, the hierarchy or the mass dependence of flow. And so this led then to the notion that the RIC collider indeed serves the perfect fluid in gold-gold collisions. And then there was this notion that how can a medium be so opaque and strongly interacting and yet have almost perfect fluidity? So this was a big announcement and made the news, and in particular, it made Scientific American news. Fast forward 10 years, this was then the beginning of the ALICE experiment, first beams, and collaborators in ALICE were able to measure flow immediately, and they used several techniques. Among these were the so-called V22 and V24 that we will introduce through these two lectures. And they saw that the flow in ALICE was actually stronger than at RIC. And this also then led to a number of questions. Why is that? And how can we understand that? And people also looked at this in CMS from a slightly different perspective, using two-particle correlation. And they saw that this flow is present not only in the so-called mid-rapidity region, near rapidity equals 0, but also over a very wide range of difference in particle rapidities. So you can see this modulation in delta phi is a signature of flow. And so this then led to the notion that we are producing a system that expands indeed longitudinally, and this system is flowing transversely. So this was a remarkable observation, a remarkable achievement. Okay. So what is collective flow? I mean, I've given you some examples of this, but let's talk about this in more technical detail, if you will. So collective flow, or simply called flow, is defined as the collective motion of particles that are produced in AA collisions, perhaps even in PP collision, proton-proton. And this collective motion is determined only solely by the geometry of the collision. This is a definition. This is how we define the notion of anisotropic flow or collective flow. As I've already alluded to, this collective flow or this collectivity is driven by the internal pressure gradients present in the system as it is created by the collision of nuclei. This is one source of collectivity. There's another source of collectivity, which is that if you have very hard collisions creating very high PT partons, as these partons penetrate through the medium, they can actually lose energy, and as such, they can be stopped or slowed down. This leads then to what we know as differential absorption. So to illustrate this, here a picture that you have a particle that would be produced here, and this particle is produced essentially the speed of light. It wants to go out, but it has to penetrate through this high density region in the so-called participant region. The spectators, I should point out, in green and in red are essentially traveling at the speed of light. So by the time this medium is formed, the spectators have gone out of the picture. They're gone down the beam pipe, so to speak. And so we are left with this, this overlap here, this almond-shaped overlap. And as I said, this overlap has a very high density and pressure gradient. And so it will expand longitudinally as well as transversely. And so this is one of the sources of collectivity of flow, the internal pressure gradient. And the other source is the fact that you can have very hard interaction producing multi-GeV particles that will have to penetrate through this, this medium before it actually expands and eventually freezes out. So these particles will lose energy, and this will lead to a sort of collectivity at higher PT. So typically, these collisions now are described in terms of hydrodynamical model, which assume fully thermalized and formally equilibrated system. And this is very convenient because the mathematics that is involved into doing this is, although complicated, it has been solved, and it can be calculated on a computer. But until the first days of Rick and the first days of LHC measurements, it wasn't clear whether this either limit was actually achieved, and there is good indication that it is in lead and at LHC and AA, or gold, I should say, at RIC. Even if such a limit is not achieved, it should be stressed that because this overlap region is asymmetric spatially, momentum transfer between particles, collisions in momentum transfer would also lead to collectivity, although it would not be hydrodynamic or saturated. And this may well be happening in PP collisions or PA collisions. So, so we have large and asymmetric pressure gradients. This leads to the expansion. And this expansion means then that the particles that will be produced will have a large momentum anisotropy. So because you have the largest expansion or the fastest expansion in the z direction, you will have the largest momentum in the z direction. And because the expansion along the reaction plane, x, here in this slide, in this picture, is largest in this direction, the momentum, the acceleration of the particle, the momentum, and the number of particles produced will be the largest along x, and slightly smaller along y. So this leads to an anisotropy, an imbalance, if you will, or a non-isotropic distribution of particles in the transverse plane. And the idea of measuring flow is to quantify this anisotropy. By quantifying this anisotropy, one is able to obtain a signature of the expansion and obtain, and then from there, the hydrodynamics will give us a mechanism to explain the conversion of pressure gradient or density gradients, pressure gradient into the acceleration of the particles. And so the physics lies in this acceleration and converting the anisotropy, the spatial anisotropy, into momentum anisotropy. And so understanding and measuring flow enables us then to go back in time and understand what happened in these collisions and what is the physics, what is the equation of state of the matter capable of driving this expansion. So I've already said much of this already, but I want to reiterate that there are two basic types of collective motion, one driven by the acceleration, the expansion of the system, schematically illustrated on the left, and one driven by the absorption or the energy loss of high momentum particles. So the acceleration of the medium, the expansion of the medium, will dominate what is observed at low PT for low PT particles, basically less than or about 2 GeV, and the absorption of high PT particles by the medium, by the spatially anisotropic medium, will dominate at higher momentum, so maybe above 3 or so GeV. So I've already said this. We believe that we have a fully equilibrated system, and this is born about from the observation already at RIC that the V2 was matching basically the expectation of a hydrodynamic system in the largest multiplicity collisions. But flow collectivity would happen even if the system is not fully equilibrated. It would happen just because of momentum transfer. And one of the big issue when we do deal with PP collisions or PA, PLED, and so on collisions is to find out whether or not this full equilibration is realized. Either way, we can have collectivity, we can have collective flow and absorption. What is not clear is whether we have this full equilibration. If the equilibration is full, then we can use the tools of thermodynamics and in particular hydrodynamics. If the terminalization is not full, then it's a little more complicated. And that's why people like to assume somehow that terminalization is complete. Okay. So what are our ultimate goals? Our ultimate goal is not to measure these coefficients, these flow coefficients, but it is to use the magnitude of these coefficients to understand the response of the system. As I said, we have two nuclei coming in with vast amount of kinetic energy, is almost at the speed of light. And they convert through the collisions, they convert some of that energy into making a very high density system with amazing pressure gradients. And so these pressure gradients are driving the expansion of the system. And so we want to understand what are the properties of this nuclear matter that enable this conversion and the degree to which it enables this conversion. And so effectively, we can ask, what are the relevant degrees of freedom? Are they hadronic or partonic QGP-like, quarks and gluons? And what is the equation of state? How is the pressure related to the temperature and so on and so forth? And then when we do this, then we end up realizing that there are properties of this matter that might be irrelevant, one of which is the so-called shear viscosity, how layers of a fluid rub against one another, so to speak, as the system expands. Another is how the bulk viscosity, how the expansion in volume might be slowed by friction. And perhaps there are other properties that matter here. But from the onset, these are the big questions that we asked. These are the big questions that the community wanted to answer at the onset of RIC and then later on at the LHC. So I think I've already said this already, so let me skip and go on. All right, so we want to measure flow. And I've already defined what we call collective flow. That is how the distribution of emitted particle relates to the geometry of the collisions. And so how are we going to do this quantitatively is what I want to discuss next. And so again, let me bring this back on this schematic picture, but now I'm going to look at this in steps. Before the collisions, this is what we see when one nucleus is coming from the left, the other is coming from the right, and there is some impact parameter between the two. And as they interpenetrate one another, there is the overlapping region, the participant region, and then there are spectator regions. The spectators will just move forward at nearly the speed of light, this way and that way. But in the participant region, the conversion of kinetic energy leads to the creation of a quote-unquote fireball. And it is this fireball that is now of interest to us. It's good to point out that the crossing time or the traversing time here is very short, because the gamma factor that we're talking about here for the contraction of these pancakes is larger than 1,000, 10,000 actually. And so the crossing time is very, very short. The redistribution, or if you will, terminalization of the energy release in the collision is believed to thermalize or equilibrate very, very quickly. How quickly is still somewhat of a matter of debate, but it's less than a Fermi over C. And then as the system expands, this fireball will stick together for a little while. And this is one can guesstimate by geometric argument that it's going to be of the order of 10 Fermi over C. And so this is what we think is happening. So again, we have the participants in the middle. The impact parameter is from center to center. And in general, this impact parameter is non-zero and forms what we call the reaction plane of the collision. And so if we have, let's say, gold on gold or lead on lead, we have this symmetric overlap region, at least on average. And the size of this overlap will evidently depend on the impact parameter. The smaller the impact parameter, the larger this overlap region will be. Okay. So now we're going to measure particles. So we have to introduce a little bit of physics and mathematics. We're going to talk about particle densities, probability densities, and so on. And so particle density will be defined. I'm going to use the notation ρ1, which can be expressed as a function of the rapidity y, the azimuth of production, and the transverse momentum of the particle. That's basically what we call the invariant cross-section of the particle production. We can integrate this and obtain quantities that are dependent on y and pt, and we can integrate this further. And what you find is that within a certain acceptance that I will call omega here, then this integration will give you the number of particles that are produced in the acceptance of interest. I can also formulate this in terms of probability, if not particle density, but probability density if I divide this density by the number of particles. So this is single particle. When we get to, first we will use single particle densities to define flow, but eventually we will, when we come to formulating more advanced technique, quote unquote, we will invoke 2, 3, 4, 5 particle densities. So it's good to have a notation for that as well. So in the case of pair densities, we introduce that we will use the notation rho 2, which now depends on the momentum of the first and the second particle of a pair. And in a collision, if you have a collision that produces 1,000 particles and you measure 1,000 particles, that means you will have 1,000 times 1,000 minus 1 pairs. And so that's a lot of pairs that are to be considered. When you integrate this density, you will get this so-called average number of pairs, n, the average of n, the number of particles, times n minus 1. If I gave you a theory for the particle production, I would give you a formula for rho 2, which you would integrate, and it would give you a number of pairs. Experimentally, in any given collisions, we're sampling, so to speak, this density. We're not seeing the full density. We're going to be witnessing fluctuations of the particle production. So what we are seeing experimentally is an average of the number of pairs. And just like that, we also see an average of the number of particles produced inside the acceptance. So this is for pairs. I can do the same. I can introduce the same notation for triplets and quadruplets and so on and so forth. And so for triplets, it would be a differential cross-section in terms of P1, P2, and P3, and so on and so forth. All right. So now that I have an expression for single particle density, I can think in terms of I can think of a technical definition for the transverse plane anisotropic flow. So what we do is that we define that the single particle emission that I introduced on the 2 slides ago is entirely determined by the azimuthal angle relative to the reaction plane, RP. And this will consider inside some acceptance that, again, I call omega. So when I integrate this this particle, single particle density, I will only care about phi, the angle of emission of the particle. This distribution, which I will now call P, probability of phi, will be modeled according to this expression here. Psi sub n will be the orientation of the reaction plane, as illustrated here. And so we're measuring this in the lab, obviously. So X lab and Y lab, but the collisions are not are random, right? We cannot control at which angle the 2 nuclei that collide will be encountering one another. And so the orientation of the 2 nuclei as they collide in the lab will be stochastic, will be completely random. And so the orientation of the reaction plane, which is this line here, will be random in the lab frame. So the angle of this angle psi is what we call the angle of the reaction plane relative to the lab frame. So we're now going to say, okay, the particle distribution relative to the lab or relative to the reaction plane is going to be determined by is going to be described by this angle phi. And we're going to model the distribution of the particles in the lab frame, and consequently also in the lab frame, according to this so-called Fourier decomposition. This is the Fourier decomposition that Sergei Voloshin introduced already at the beginning of the Rick era. Within this Fourier decomposition, we have these coefficients v sub n, n going from 1 to possibly infinity, but in practice, the coefficients of order 2 and 3 will dominate. 4 is finite, but when you go beyond 5 and such, then these coefficients become typically very, very small. You will, this factor of 1 to pi here is for normalization purposes, and the factor of 2 here, you will see, is introduced to lead to a sensible normalization of these coefficients, as I will explain in a moment. So evidently, if I now take this expression and I were to integrate this expression over all angles phi from 0 to 2 pi, then I would have a contribution from the first term, right? So the first term would give me a factor of 2 pi divided by 2 pi, and that will give me this value 1 here. The second term is going to be integrated from 0 to 2 pi as well. The integral of the cosine of phi, oops, I realized there's a factor of n missing here. So what's inside here should be multiplied by n. I apologize for that. And so, be that as it may, this cosine here, the average or integral of the cosine from 0 to 2 pi will vanish, and will indeed be will end up with 1. It strikes me now that I might have forgotten to put this factor of n in more than one slide, so I really apologize. It's embarrassing. Okay, be that as it may, we now have these. So we have now a technical definitions for what these coefficients will be, and with this technical definition comes a common nomenclature that is now pretty much universally accepted and used in the community. So V1 is going to be called directed flow. V2 is known as elliptic flow. V3 triangular, and V4 quadrangular flow. Technically the angle psi sub n should correspond to the reaction plane. In practice, when you measure such things, they may differ from one another because of fluctuations and a number of other considerations. This on the right here illustrates what the system could look like spatially, so to speak, if you have a specific value of these coefficients. This is yet another way of looking at this, just to emphasize that we have spectators that are in blue here. These spectators travel at the speed of light, and basically, given that they are traveling at such high momentum, they have essentially the nucleons in here have a de Broglie or de Broglie wavelength that is very, very small compared to the size of the system. And so these nucleons and quarks or gluons present in the spectators basically are passing by so fast that they are not aware of what happened to the rest of the system. And we then have this overlap region that now has a large energy density and a large pressure gradient, and that will lead to radial flow, as illustrated schematically here, as well as elliptic flow and directed flow, and to some extent also triangular and quadrangular. So I want to emphasize that what we have is a technical definition of what we call flow. And associated with this technical definition, we can consider a system that would be purely flow. And what I mean by this is that a system involving, let's say, m particles that would involve no correlation whatsoever between them. So pions and kaons that would be produced essentially independently of one another, except for the fact that their direction of production is driven by the geometry. So this is what we call pure flow. And evidently what we're seeing is that we are going to see additional contribution to the particle correlation, leading to what we call non-flow. So the first thing we can ask is, what is the magnitude of these coefficients? And we will, with the understanding that the magnitude of this coefficient is driven by the physics of the collisions and the conditions of the matter in these collisions. So evidently, if the psi coefficients were known, we can calculate the magnitude of the coefficients by just calculating the average of the cosine here. And thankfully, I have the n here. Or n or m, depending. And so the average of this, or the expectation value of this, is just 1/2 pi, the integral, and then the cosine times the distribution of the flowing particles. So we can calculate, so these Vn here will be called the integral flow coefficient. And to calculate this, we can remember the orthogonality relation of cosines and sine, which you, I'm sure, remember, as shown here. And then we can use these orthogonality relations then to calculate the integral, the expectation value of the cosine. And what you find is that when you do this, only the first term, only one term rather, will contribute, and that leads to the notion that this expectation value then equals the magnitude of the coefficient v sub m. So these v sub m are called integral flow coefficient. Now, evidently, to do this, we need the orientation of psi, and psi is not known a priori, so we will have either to measure it somehow, collision by collision, or extract the Vn by some other means. And so this is the story of the development of flow measurement techniques over the last 24 years. Before I get into this, and I realize I'm going to run out of time, so I've spoken of a Fourier decomposition, and you may have noticed that my Fourier decomposition only involved cosines terms, not sine. In general, when we write a Fourier decomposition, we involve both cosine and sine terms. But the Fourier decomposition I used, and is used now, which is used by all people, is a Fourier decomposition that does not involve sine terms. Where does that stem from? Well, it stems from the fact that in a collision, on average, when you have two equal sized nuclei, this overlap region is symmetric by construction. It's ideally, idealized collision geometry is symmetric. And so then this obviates the necessity for sine terms. They just vanish. In practice, what we have, and this was realized through the RIC program by these two gentlemen here, Alvar and Roland, what they realize is that when you collide nuclei, the nucleons inside, or perhaps the partons inside, are going to collapse their wave function as they at the impact. And so what we are going to measure is a distribution of energy at the onset that may not be symmetric. It will depend on where these partons or nucleons are actually interacting with one another. And so in this cartoon here, you see that in a given collision, this interaction and this collapse of the parton or nucleon wave functions may not be aligned perpendicular to the reaction plane. But when you do a Fourier decomposition, you can always rotate your Fourier decomposition to consider a system that would be symmetric. And this leads to the notion then that we can introduce a so-called participant plane, relative to which the sign Fourier decomposition would vanish, and we would be left only with cosines. But then we have this idea that when we collide a nuclei, what matters is not so much the reaction plane on an event-by-event basis, but it's in fact the so-called participant plane. And if we really want to understand the magnitude of the coefficients that we observe, we really have to do this in the context of the participant plane. So I've said all of this. So there are many challenges in these measurements. Some challenges have to do with the fact that we are not measuring the reaction plane directly, as I just said. And so we will have, and obviously we're not measuring this psi, this angle of the reaction plane, or even the participant plane, explicitly on an event basis. So we have to devise methods to either measure this psi, or estimate the psi, or find techniques that would not depend, techniques to calculate or measure the flow that would not depend on the value of psi, but would only depend on the angle of the particles. And so that's what we're going to do. Another challenge that is worth mentioning is that when we look at cartoons, we see, when we can visualize what's going on, but in reality, for most of the collisions that we observe, these Vn coefficients are very small, or relatively small, and so that means in practice that our capacity to measure them will be weak. So if we wanted to measure these coefficients on a collision by collision basis, or accuracy or statistical uncertainty would, it's been evaluated, would go essentially 1 over square root of 2n, n being the number of particles involved. And so for a large number of particles, or for a small number of particles rather, this statistical uncertainty is actually very, very large. When you get to a very large system with large multiplicity, then you get some relief, and you get decent measurement precision, but essentially you cannot, from one collision alone, determine with very high accuracy these flow coefficients. So what that means in practice is that we have to average over many collisions. A lot of the techniques that we're going to talk about involve the difference between phi1 pairs, the phi of particles of a pair, phi I and phi j, and evidently this this will mean that we need to understand the acceptance and correct for efficiencies and that sort of thing. Now, if we rely on this, it means that we are going to see correlations that are due not only to the geometry of the collisions, but also to other phenomena such as resonance decay, jet fragmentation, and so on and so forth. And contribution from these decays and jet fragmentation will also involve correlations between particles of a pair, or triplets and quadruplets and so on. And so that means that there will be a contribution to the correlations, or the correlation functions, that are not associated with the geometry, and we will call these non-flow, and we will denote these according to the delta symbol sub n. And so in general, when we talk about flow, we will look at the expectation value of the difference of of a pair, phi I, phi sub j, and we will say this will correspond to the average, or the expectation value of Vn square, and then there will be a contribution from non-flow, and generally it's expected that, or understood that these two contributions are statistically independent of one another, so they are added linearly here. Now, when we measure flow, we will wish to suppress this value of delta. In other words, we will wish to suppress non-flow contribution. And so techniques have been introduced to do this. Another challenge arises from the stochastic nature of these collisions. So for every collisions, the orientation of the systems will be at some angle, and we will need to account for that and account for the fact that as the system collides, and there will be different densities locally, and the expansion then will be might change. So eventually, what that means in practice is that there will be fluctuations in the amount of flow. There is collision by collision. So this leads to the notion of flow fluctuations, and we will characterize this flow of fluctuation, these flow fluctuations, in terms of a variance. And the variance is, by definition, the expectation value of the square minus the square of the expectation value. So at the end of the day, when we measure flow, we have contribution from the flow we wish to measure, the actual geometry-driven flow. We have flow fluctuations, and we have non-flow contributions as well. I'm going to run out of time. Give me another 5 minutes, and I will. You can. All right. So I see that we're not going to get to measuring, actually discussing actual techniques today, but I want to finish by first talking about the geometry itself. What I've said is that we want to measure the expansion of the system and characterize it with these flow coefficients. But for these coefficients to be meaningful, we need to understand what is the geometry. And so, in other words, we need to be able to characterize the geometry of the system itself at the onset of the collision. This is hard to do, and there are techniques to try to access that information, HBT and such. But in general, this is difficult to do. And what we end up doing in practice is to do models of the geometry of the system. And so these models will give us what is called the eccentricity, or the spatial eccentricity, or the ellipticity of the source. And so this initial spatial anisotropy will depend on the elongation of the system. And there were papers already dating to 92 how to calculate such things. And then there were papers that realized that when you have a when you take into account the fact that we're dealing with nucleons or partons, then the story is not as simple. So the notion of eccentricity is actually a little bit more complicated. So I would recommend reading these papers for that purpose. So let me cut to the chase when it comes to the eccentricity. The eccentricity is defined as the expectation in terms of these expectation value. So the variance, or if you will, the width in X of the overlap or the participant region, the width in Y of this participant region, and sort of a covariance of the two. And so this then gives us a measure of how elliptical or how spatially anisotropic the matter is. If we know the impact parameter and we know approximately the geometry of the nuclei, we can calculate this ab initio with some models, for instance, Monte Carlo Glauber models. How do we know the impact parameter? Well, we cannot. Again, we don't measure the impact parameter directly, but we can have a proxy based on the multiplicity of the collisions, which is not something that I'm going to really talk about today. And so at the end of the day, we can evaluate the eccentricity of, or the so-called reaction plane eccentricity based on formulas such as this one. And so that means that when we collide particle nuclei at a given impact parameter, we know what the eccentricity is. We know what the Vn coefficients are, and so then we can ask ourselves, what is the relation between these eccentricities and the coefficients? Let me skip. And so this is our program, and well, I am actually out of time. So this may so next time we will actually introduce actual techniques, and we will discuss some of the basic techniques and some of the most advanced techniques that are used in measuring flow. Somehow I realize I'm a little verbose here, and I have not been able to reach that point, but I feel that to really understand what flow is, it was necessary to introduce each of the concepts that I've covered so far. Let me stop here and ask if you have any questions on the materials I've covered so far.
Thank you so much, Claude. This is Ramni here. This was really a wonderful presentation, starting from scratch about the flow. And everyone knows that this is not a small topic to be covered in 1 hour, but you have tried very well, giving the basics right from what is the definition of the different types of flow, what is flow, why we require, and especially the challenges part. Challenges which are there with the thank you formally, and we close. It's very important to take up the questions, and I invite now the participants and solutions one by one. Was I audible?